Hi everyone, in this video we are going to see about Wien bridge oscillator using op-amp. An oscillator is an electronic circuit that generates a periodic waveform. It can be a sine waveform, square or a triangular waveform without any external input signal. So in the previous videos, we have seen about the Astable multivibrator or the relaxation oscillator which can be used as a square wave generator. So in this video, we are going to see about the sine wave oscillators. Oscillators are amplifiers with positive feedback circuit. This is the amplifier. A part of the output is fed back to the input. Here we can see the plus sign which indicates that it is a positive feedback circuit. The important thing about oscillator is that it does not need any external input. It generates sinusoidal waveform by itself. How this is possible? When op-amp is used as an amplifier, we used to give plus or minus 15 volts as the power supply for the op-amp. That DC power supply is sufficient to produce the sustained oscillations at the output of the oscillator. When you give the DC power supply, a small disturbance or a noise will be generated in the circuit which gets amplified because of this positive feedback circuit. So the amplification takes place till we get a sustained oscillations at the output. For that, one important thing is that this feedback circuit will be designed as a frequency selective circuit. Only that particular frequency of the noise will be amplified while the other signals will be rejected. So this frequency selective circuit determines the frequency of the output oscillations. So only that particular frequency alone gets amplified and you will get at the output. Is it easy to get a sustained oscillation? No, because we need to satisfy some conditions to get the waveform like this. The criteria is given by Barkhausen Criterion. The first one states that the total loop gain, that is the amplifier and the feedback circuit, the total loop gain should be equal to 1. What does it mean? This waveform, particular waveform has A beta equal to 1. In case my A into beta, gain product is less than 1, the oscillations will be decreasing in magnitude and soon it will die out. In case if A beta is greater than 1, the magnitude of the sine wave will be increasing and at one time it leads to instability, or we can say it gets saturated because of the power supply voltage of this op-amp. The second condition is that the total phase shift around the loop, this angle A beta should be equal to 0 or it can be 360 degree. Only if these two conditions are satisfied, you will get the sustained oscillations at the output. Let us see about the types of sinusoidal oscillator. According to the frequency range, it is classified as RC oscillators and LC oscillators. In RC oscillators, it can be used in audio frequency range. There are two types. One is the RC phase shift oscillator, which we saw in the previous video. And in this video, we are going to see about the Wien bridge oscillator. What is a Wien bridge oscillator? So it is a type of electronic oscillator that generates sine waves. Why it is called Wien bridge oscillator? Because in this the feedback circuit consists of a Wien bridge. So what is Wien bridge? Similar to the Wheatstone bridge, Wien bridge is also a circuit used to measure the capacitance in terms of frequency. So here in this Wien bridge oscillator, this Wien bridge is used as a feedback circuit. This is the circuit diagram of a Wien bridge oscillator. So we can redraw this circuit so that it will be easy to analyze for us. So the same circuit I have drawn like this. If you see, to the negative terminal of the op-amp, R4 and R3 are connected, but R3 is grounded. So this is R3, it is grounded. R4, the other end of R4 should be connected to V0. So basically R4 is the feedback resistor. So this I have connected here. Then to the plus terminal, what is connected? The parallel branch is connected. So to the plus terminal I have connected the parallel branch. The other end should be connected to ground. Then the series branch, the series RC branch is connected between plus terminal and R4. So plus terminal is here and R4, this terminal is connected. So the circuit is same, but we have redrawn like this. So here you can observe certain things. So here the plus terminal, we are connecting the feedback. So the op-amp is in non-inverting mode. And this circuit consists of 4 resistors and 2 capacitors. So this is the feedback network for non-inverting amplifier. The gain is 1 plus R4 by R3. And for the feedback network beta, it is output is VF, input is V0. So VF by V0. Now we have to find what is VF and V0 relation. Let us look at the feedback circuit. Here we have this series R1 and C1. If you see the capacitive reactance, X is equal to 1 by omega C. Omega is nothing but 2 pi F. So frequency is inversely proportional to the reactance. At low frequencies, this capacitive reactance is very high because F is low, Xc will be very high. So it doesn't allow the low frequency signal. Basically, it is a high pass filter. Similarly, if you see here, at high frequencies, this Xc2 is very low. Basically, it acts as a short circuit. So this is a low pass filter. So this combination, high pass filter, low pass filter, in between there will be a frequency where it will act as a band pass filter with a resonant frequency Fr. So at that resonant frequency, the output will be maximum. So another thing, at resonant frequency, Xc will be equal to R. So there is no phase shift here or no phase delay between the input and output in the circuit, because already op-amp is in non-inverting mode. So there is no phase difference between the input and output. So feedback circuit also doesn't give you any phase difference because it is operated in resonant frequency. Now first let us take this series combination as impedance as Z1. So these two are in series. So R1 plus Xc1. Xc is nothing but 1 by omega j omega C1. So simplify it. This is Z1. Now let us take this R2 C2 which is in parallel as impedance as Z2. So R2 into 1 by j omega C2 divided by R2 plus 1 by j omega C2, because these two are in parallel. So simplify it, you will get Z2. Now VF, what is VF? So VF is the feedback voltage, this voltage. The other end of this impedance is connected to ground, and here we have V0. So we can write VF is equal to V0 into this impedance divided by sum of these two impedance. So Z2 divided by Z1 plus Z2. So this one, for my convenience, I am writing it as M. This part alone. Z2 divided by Z1 plus Z2. I am writing as M. If you want, you keep it as such and do the derivation. Since I don't have enough space, I have simplified it to term M. Now let us find what is this M. So M is equal to Z2, this part, divided by Z1 plus Z2. So add these two. So here you can see I am keeping the numerator as such. This part you multiply by here and this part gets multiplied with this. So denominator you have two parts. So actually this part and this part are same. So let us cancel these two, and you have to do the simplification here. Just multiply by each term and simplify it. You will get this one. So this j omega C1 I can bring it to top numerator. So numerator I will have this one. You multiply all these things So when you are multiplying, you should remember one thing, j into j will become j square is equal to minus 1. So for this particular multiplication, you will get minus here, minus omega square C1, C2, R1, R2 plus this term. Now we can split the real part and imaginary part. So I am bringing this term here and j part this side. Now actually if I divide by this one, this j omega will cancel. Actually this j omega will be here. So this is actually the imaginary part. So equate the imaginary part to 0. So this part is equal to 0. From that we can find what is omega square. If you know omega, you can find what is frequency. So this root is for all the variables C1, C2, R1, R2, everything. So this is the resonant frequency. But for simplification, we can take R1 equal to R2 equal to R and C1 equal to C2 is equal to C. So in such a case, the resonant frequency is given by 1 by 2 pi RC. And now again we will find M. M is equal to, take the real part alone. So you will get this one. And with this assumption, R1, R2 is equal to R. So M becomes 1 by 3. What is M? Z2 divided by Z1 plus Z2 is the M. So M is equal to 1 by 3. Now you substitute in this equation, you will get beta as 1 by 3. So for sustained oscillation, we know A beta is equal to 1. Since beta is equal to 1 by 3, A should be equal to greater than or equal to 3. Since this is a non-inverting amplifier, the gain is given by 1 plus Rf by R3, that is equal to 3. So from this you can find relation between R4 and R3 is equal to, R4 is equal to 2 times R3. So this is how you have to design the Wien bridge oscillator. So the points to remember here are, an oscillator is an electronic circuit that generates a periodic waveform without any external input signal. According to Barkhausen Criterion, A beta should be equal to 1 and the phase angle A beta is equal to 0 degree or 360 degree. In Wien bridge oscillator, an op-amp is operating in the non-inverting mode and Wien bridge is used as a feedback network. So in both these cases, there is no phase shift. And the voltage gain of the amplifier for sustained oscillation should be greater than or equal to 3. If you like the video, do subscribe to Read Electric Vehicle channel. Thank you.